Okay, so guys, for some of you, you're going to feel like today is going to be a whole big old string of deja vu. And in some ways, frankly, it is. Because guys, we did chemical equilibrium last year. What we're going to do today is even go back to the place where I introduced chemical equilibrium to you last year. Remember this hypnotic little game? Okay, so guys, we're going to do that again today. And guys, maybe you picked up on this last year. I suspect you guys are the kind of people that might have. You may have noticed that when I did this demonstration with you last year, I was skirting a lot of your questions, and frankly, and I was aware of it if you weren't, there were certainly points in this demonstration where your questions were sort of bringing me up short because I wasn't sure how to answer them. Guys, it wasn't because I didn't know the answers, it's because I didn't want to tell you the answers, because in general chemistry, you didn't know enough to know what you weren't capable of knowing. Right. So, what is it that makes us better able to play the tube blue food coloring water game? What is it that makes us better able to play this game right now than you were almost 12 months ago? And guys, the answer is you understand rate. And because you understand rate, you can have a much more intelligent interaction with this thing. Now guys, this is the beauty of this. If we were to consider this an analogy, guys, good analogies only get better as we dig into them deeper. And this is a good analogy because what you're going to find out is the more we try to pick this apart, frankly, the better it holds up. Certainly you are going to find some shortcomings to this, but guys, you're going to find out that given what you now understand about rate, this actually gets stronger and not weaker. So we're going to start there. Then guys, what we're going to do is we are going to start picking equilibrium apart and talking about the details of this, many of which are review from last year in greater detail, some of which will be new. To be honest with you though, we probably won't get done today. It doesn't mean that we're not going to do on Tuesday or on Friday, what we were planning on doing, but there's going to be one little concept that we may not get to that we'll just throw on the front of Friday, and then we'll do what we were going to do Friday anyway. So, guys, with all of that said, we are going to start by reviewing a little bit. So you ready? I know you guys are dedicated note takers, so we'll go slow. So here we go. Guys, when a system comes to equilibrium, what's going on? First of all, maybe we should ask this. What kind of systems can come to equilibrium? Well, not that specifically. They go both ways. Guys, these are called, you know the term, reversible reactions. These are reactions that do in fact have the ability to go both ways. Now guys, what is the opposite of a reversible reaction? There's a name for those reactions. No. Okay, so it is irreversible, but there's a bigger, more general term that we use. No, they're called quantitative reactions. Do you remember that term from last year? I didn't put it in the notes, but maybe we should do this. So guys, reversible, that's cool you guys made that connection. Let's bring it all together. So guys, reversible reactions are reactions that go both ways simultaneously. Eventually they end up at equilibrium. The opposite of that is what is called a quantitative reaction. Why do we call it quantitative? Because it consumes the entire quantity of one of the reactants. Which reactant gets consumed completely? The limiting reactant. Remember all of this? Maybe you don't. If you don't, write it down, get it back in your brain, or at least on paper. But guys, what do you now know to be true about quantitative reactions? They're irreversible and therefore spontaneous. It's cool you made that connection. I wasn't planning on going there, and it's neat that you did. But guys, the generic terms for these are reversible and quantitative. Quantitative reactions go to completion. They consume the entire quantity of the limiting reactant. You also, as you pointed out, understand that those are spontaneous and therefore irreversible. Is it all coming back to you? Bits and pieces. So guys, what happens when these things reach equilibrium? Well guys, the idea is this. We have reversible processes, and these things are happening simultaneously, moving forward and back. When this thing reaches equilibrium, the rates become the same. And guys, it's at this point that you should have, because I gave this to you last year, and you just wrote it down. This year should be different, because the minute you write down the word rate, you should have a very rich experience given what you learned in chapter 14 and what we've been doing over the last 4 class periods. Because rate for you is no longer just a term that means how fast the reaction's going. Because now you understand rate laws. Now you understand the molecularity of elementary steps. Now you understand mechanisms. Now you understand how rate is concentration dependent, meaning that reactions are always slowing down because the reactants are always getting consumed. And you know how to figure out rate laws, and you understand reaction orders. And all of those concepts, guys, are tied up inside that one little bitty term at the end of this sentence. So what we get to do today is we get to bring all of chapter 14 forward and use it to inform our understanding of equilibrium. And we're going to do that in just a minute. So guys, what does this actually look like then when it reaches equilibrium? And the answer is this. At equilibrium then, the rate at which the reactants are turning into products becomes equal to the rate at which the products are turning back into reactants. Y'all caught up with me? You okay? So guys, here's what we're going to do then. Write this down with me. I would encourage you to skip down 3 lines and make it as wide as your paper. Do it big. You're going to need some space to write around this. You good? Okay. So guys, with that done, here's what I need you to do. Write down the rate laws for the forward and reverse reactions, assuming that this entire process is elementary and therefore doesn't have anything going on in the background. Again, it's a generic example, as Everett and I were talking about while we were grading homework. When we do generic examples, we can make up realities that may not even exist. So, reactants simply turn into products. We don't need to know what they are. We can still write rate laws. So guys, write the rate, and here's what I want you to do. Write the rate law for the forward reaction above the reaction, and then write the rate law for the reverse reaction below it. And then guys, assuming that my board's going to cooperate, I'll actually do this with you. Interestingly, my board is behaving very well. I think it's kind of like my dog. I think my dog got the sense that there was a very real chance I was going to take it out in the backcountry and kill it. And it decided it had better behave because it knew its life was in danger. I think my board's in the same place. I think it knows its days are few. And I'm looking to get a new one, and it's behaving well, hoping that I won't put it out to pasture. Yeah, it is actually the radar one. Yeah, I ordered it on Friday. So, what's that? Okay, guys, here we go. So let's talk about rate laws. So we understand that when we write rate laws, this is always rate is equal to. What's the first thing that comes into a rate law? K. Now we've got to do this. Oh, come on, baby. This is what we are going to call K forward. Because, guys, you're going to find out the K values for the forward and reverse reactions are not the same. So, what else then belongs in the rate law for the forward reaction? Concentration of the reactant. So we'll put RCT for reactant, and that then defines the rate law for the forward reaction. So guys, summarizing to drive home the point, what then is the rate of the forward reaction dependent upon? The value of K, which is dependent upon what? No. The value of K, which is dependent on what? Temperature, surface area, catalyst, those sorts of things. And then, guys, what's the other thing that the rate is dependent upon? The concentration of the reactant. Okay. Then, guys, and you know what? While we're at it, why don't we get really specific and call this rate sub F, because it's the forward rate. So now let me give you a second to doctor up what you wrote below the line, given what we just wrote together above the line. Most of you right now are sneaking in little r's. So now let's talk. So guys, now what we've got is the rate of the reverse reaction. And that is going to be equal to K, but it's the reverse process. And then, this is kind of weird, what is our reactant in the reverse process? The product. So it is also then dependent upon the concentration of the product. You good? Okay, so now guys, what we're going to do is, given this more complete understanding of what's going on, we are going to repeat this little demonstration that I did for you last year. Now, I know that some of you didn't have me last year. For those of you that, have you all seen this before? Have any of you not? No? Okay. So guys, with that said then, doing this again, guys, what I want you to do is I want you to be thinking, given my new understandings, given the things I learned in chapter 14, given this information that now makes a whole lot of sense to me, how does this demonstration get even better? You ready? So you may remember the blue water simply represents all of the mass present in this reaction. If it's in this tube, it represents reactant. If it is in this tube, it represents product. Okay, so now guys, let's talk about all of our analogies. You ready? So, what in this demonstration, and guys, this goes back to our initial thing up here, what in this demonstration is analogous to concentration? Say it again. How much water is in the tube? So guys, are you guys seriously passing notes? So the answer is yes. So guys, the idea here is we need to figure out where these analogies lie. So what is analogous to the concentration of the reactants and products? And the answer is volume. So right now you can see in this tube we have a very high concentration of reactant. And what is our concentration of product? It's 0, right? Now let's see if we can continue to unpack the analogies. So guys, we have now identified this portion of the analogy. We now know where that is. So guys, what about this? Where are the K values in the analogy? In this setup, what represents the Ks? Say it again, Nate. The tubes. Guys, I told you last year that these tubes represent rate. That's not true. These tubes do not represent rate. These tubes represent the rate constant. And guys, this is one of the things that makes this really hard to do with general chemistry students, is because you can see that for some of them, the wheels are turning and they're going, wait a minute, this doesn't quite jive and I don't understand why. But guys, these tubes do not represent rate. These tubes represent K. So now we have identified these things. Now let's talk about, you okay? I do. Oh, they're gone. If you need to run to the bathroom, you can. So guys, now let's talk about this. What then represents rate? Well, guys, let's talk about how we find it mathematically. In order to find rate, what we do is we multiply concentration times K, right? Where does that multiplication happen in the demonstration? When you dip it. Guys, check this out. The dipping is analogous to multiplying. So guys, what we're going to do is the big tube is going to represent K forward and the small tube is going to represent K reverse. Okay, now watch, because this gets really good. So take a look. What does this represent? The concentration of reactants. What does this represent? The K forward. And so when we have a high concentration of reactant and when we have a large K forward, we have a lot of reactant turning into product. So what actually represents the rate is the amount of water in this tube being converted to product. So initially, we have got a very, very high forward rate because we've got a lot of reactant and we've got a large value for K. Now guys, watch. As this reaction continues, what is happening to the rate? It's slowing down. What in this demonstration represents the rate slowing down? The amount of water inside the tube. Why is the amount of water inside the tube going down each successive time that I do this? There's less reactant. So guys, this little demonstration rate here clearly demonstrates the principle that you learned the very first day of this unit that says reactions are always slowing down because the concentration of the reactant is always going down. Do you see the connection there? So guys, as we go on, we see that the amount of water that we're transferring forward is decreasing. But guys, what's happening to the value of K as I do this? It's not changing. It's the same tube. K is not changing, but the rate is going down because this is decreasing. The concentration of reactant is decreasing. Do you get the idea? Because now, guys, watch this. The reverse process is just as solidly supported. Because, guys, when a reaction starts, how much product turns back into reactant? None. So what is the reverse rate initially? 0. But the question is why? Why is the reverse rate initially 0? There's no product. So guys, you know how the multiplication works. 0 times any number is 0. There's none in the tube. So guys, because our initial concentration of product is 0, the reverse rate is 0 because 0 times any value is 0 because clearly there's no product to turn back into reactant. You get it? And now guys, watch what happens, because this is where this gets even better. So initially, we have a large concentration of reactant, we have a large K value, we have a lot of reactant that turns into product. But again, what's our reverse rate? 0, because we ain't got any product to turn back into reactant. Now guys, watch what happens. As we now continue, we still have a lot of reactant turning into product. But how much compared to initially? Less. So there's less moving forward, so the forward rate goes down. But what about the reverse rate now? It's not 0 anymore because now we have a little bit of product to turn back into reactant. And now, guys, as we continue, reactant turns into product, but what's happening to the rate of the forward reaction? It's decreasing. Why? Because the amount of reactant is going down. What's happening to the reverse rate? It's increasing. Why? Because the amount of product is going up. And guys, as this reaction goes on, the forward reaction slows down, the reverse reaction speeds up because the amount of reactant is going down, the concentration of reactant is going down, the reverse reaction is speeding up because the amount of product is going up. And eventually, guys, what's happening to the amount of water inside these two tubes? They're closing in on each other, right? The amount of water moving forward, the forward rate is going down. The amount of water moving backwards is going up. And eventually we get to the point where the amount moving forward and the amount moving backward is the same. And at that point, what do we call that condition? Equilibrium. And you guys, this is sad, right? Do you remember the volumes where they balance out? None of you do? It's not double. It's 70-30. Yeah. So guys, what's going to happen is when this reaches 70-30, this is then going to balance out. So let's say that it's now, well, it may be close. It's not there yet. So let's get it there. So guys, eventually, in this case, when this reaches 70-30, this balances out. The amount that's moving forward and the amount that's moving backward is in fact equal. And at that point, the rates have become equal. And we are there now, and this is 70-30, and it's at equilibrium. You get the idea? Okay. Now, guys, let me ask you some questions. So this thing reached equilibrium at 70-30. What was it about the demonstration, and therefore about real-life chemistry? Guys, what was it about the demonstration that dictated that this was going to reach equilibrium at a 70-30 ratio? The K values. Guys, you may want to write that down. The place where equilibrium lies is determined by the values of K. Again, guys, the place where equilibrium lies is determined by the value of K. And guys, if that doesn't make sense to you, let me offer you this really quick as an explainer. Guys, check this out, and you'll probably want to do this with me, but it's going to require a clean screen in just a moment. So you're all convinced that we're at equilibrium, right? So guys, what is equal at equilibrium? The rates, the forward and reverse rates. So guys, what does that tell you at equilibrium about those two? They're equal, right? So guys, follow along with me mentally. So at equilibrium, these are equal, yes? So if these are equal, what's also true of these? They are also equal. Now guys, watch what we're going to do, and you'll probably want to do this with me. So K forward and reactants. So guys, clean screen and do this with me to drive home the point you just wrote down. So at equilibrium, the rates are equal, and therefore the other side of the equations are equal. So hopefully you would agree that it's fair, come on board, to say this is equal to this. Oh, thank you. Yes, thanks. Sometimes I struggle so much getting my board to write that I lose track of what I'm writing. Yeah. So guys, do you understand what it is that allowed us to write what we just wrote on the board? At equilibrium, the rates are equal. And if the rate side of that was equal, the other side of that is also equal, which means that these are equal. Okay. Now watch what we're going to do. We are going to solve this for this ratio. Literally, I don't have a ruler, but guys, we're going to solve it for this fraction. Products divided by reactants. So when we solve this for the product divided by reactant ratio, we are going to divide both sides by reactant, and that gives us product divided by reactant. But how do we isolate that? Well, we also divide both sides by K sub R. And now, guys, look at what we find out. This equilibrium ratio, products divided by reactants, and by the guys, do you remember from last year what we call this? Do you remember what we call products divided by reactants? KC. Remember that? You solved them last year. Maybe you don't remember. But guys, this expression has a name. It's called KC. So this KC relationship, which for our little water demo is 7/3, 70 divided by 30, is actually equal to our K value relationships for the forward and reverse processes. And guys, you can actually see that visually. This tube is 7/3 bigger than this tube. It's not quite that easy because the volume is the product of, you get the idea. But you can see that this tube is bigger, K forward. So K forward is bigger than K reverse, and therefore products are greater than reactants, and the ratio of this is dependent upon the ratio of this. Do you see how all that fits together? Now you want to have sort of a mind connecting experience. Grab your books and open to the beginning of chapter 15. Open to page 613. Look at the top of page 613. Instead of doing reactants and products, they are giving us a reaction. Your reactant is N2O4, your product is NO2. See it? Then guys, notice what they did. Down in equation 15.2, they wrote the rate of the forward reaction, K sub forward times the concentration of reactant. They wrote the rate law for the reverse reaction, K sub reverse divided by NO2 squared, assuming that it's elementary. And then guys, they came down and they said at equilibrium, looking at equation 15.4, they set the two equal. And then they solved for product divided by reactant, NO2 squared divided by N2O4. Notice they said that is then equal to the forward K value divided by the reverse K value, and that is equal to a constant, which you guys sort of identified as being Kc. So guys, they did that entire process that we just did, but did it with an actual system, which is this N2O4 turning into NO2. Now here's the $11,000 question. How many of you can honestly say that when you read this, when you reviewed chapter 15, you understood it? You just identified the difference between high school and college. Seriously, guys. What took 15 minutes and a bunch of blue food coloring water for me to help you understand, the expectation in college is that you can read this and get it just by reading it. See, all of a sudden you appreciate your good high school teachers, huh? Okay, so guys, with that said, this is the fundamental idea that all of this is then equal to Kc, and if you don't remember that, we will go back and jog your memory and remind you that Kc is the product divided by reactant ratio for a reaction that's at equilibrium. You guys okay? Yeah. No, yeah, so I haven't looked, oh, can I just steal yours? I haven't looked at this in a while. I wonder how badly they've done away with them. So guys, let's talk about it. So turn to the page 12 in your AP equation sheet. So if you want a very succinct answer to what are we going to do for the rest of the year, The answer is we're going to do the letter K. Seriously. If you look where it says equilibrium, you've got KC, KP, KA, KB, KW. That's your life for the rest of this class. Seriously. And then we're going to build a battery and call it a year. It's really that simple, guys. So here's the deal. These K values, of which we wrote KC on the board, here's what they all have in common. Ks are all equilibrium ratios of products divided by reactants. What's the difference? Well, it's the thing that we're looking at the equilibrium ratio for. So KC stands for concentration. It is the K relative to concentration. What do you suppose KP is? Gas pressures. Ka is for acids. Good for you, weak acids. Kb is for weak bases, and then Kw is for water. See, guys, that's what we're doing, and then actually the one that's not, oh boy. Wow. And then the big one that they left off is KSP, which is the K for solubility products for slightly soluble salts. So they're even missing one. But guys, really, that's what we're doing for the rest of the year is K values. So did that answer your question, Carson? Yeah. Yes, and thank you. All K values do not have units because all the units cancel. It doesn't mean they don't communicate information, and we're going to talk about that in a minute, but K values do not have units. Yep. You guys okay? All right. So now, guys, this is going to start to feel, well, do you understand why that demonstration is so hard to do with General Chem? Because there's so much you just got to hold back that you can't talk about, and really it makes you out to be a liar. Because the minute you say this tube is the forward rate and the reverse tube is and this tube's the reverse rate, the whole thing goes out the window. Because when that's not true, none of it is really representative, and it makes it sort of a hard thing to do. Okay, so guys, with that as sort of a fundamental review of equilibrium, now we need to start chipping this apart. So guys, these are the things that you need to understand about equilibrium. Of course, you will write down the things that you believe to be worth writing down. But guys, first of all, we are going to look at equilibrium graphically. And the reason that we're going to look at this graphically is because there's an important concept that you need to understand. So guys, are you all settled with the idea that this is at equilibrium? Up here in my hand. So here's the question. At equilibrium, and it sounds stupid, but guys, at equilibrium, what is equal? The rates. Guys, at equilibrium, the rates are equal. But if that's true, what does the amount of water represent inside these tubes? Concentration. And so guys, what is true of concentration at equilibrium? They're not equal. We just discovered that. They're 70-30 in this case. What is it that determines 70-30? The K ratio. But guys, the bottom line is the concentrations are not equal. So if they're not equal, what are they? Constant. They're unchanging. Guys, that is going to stay 70-30. And so let's put this in writing, if you will. So guys, when we talk about equilibrium, it's important for us to distinguish what's going on with rate and what's going on with concentration. So this is the part you got to get down. What happens to rate at equilibrium? Forward and reverse. They're equal. But guys, what happens to concentration at equilibrium? It becomes constant, unchanging. And obviously the two go hand in hand. When the rate is equal, when the rates are equal, the rate at which product is being made and the rate at which reactant is being made are the same, and therefore the concentrations wouldn't change. But guys, you've got to understand the difference. So what does this look like graphically? Well guys, check this out. Here we have the representation of our fictitious process, but instead of reactant and product, they're calling it A and B. But here's the idea. Well, let me even ask you, guys, just from looking at this from a distance, which is the reactant, A or B? How do you know A? It's going down, right? Reactants get consumed, products get made, so A is the reactant and B is the product. So guys, this is actually data from the reaction where A turns into B, but the idea is this. They're both relative to time. But notice what happens to concentration when this reaches equilibrium. Concentration stops changing. Notice what happens to rate. The rates become the same. They become superimposed. And guys, you've got to understand the difference. Yeah?
So you're saying like that reaction, when it just increases temperature, would it affect, so both K values, would they go up?
They don't. No, not necessarily. You can't count on that. And that's a great question. So if you were to change K, if you were to change temperature, the K values would not necessarily change proportionally, and therefore the concentration ratio at equilibrium can change. Yeah, that's a great question. And that's frankly what chemical engineers do. One of the things that a chemical engineer will do will find the temperature at which the creation of products is maximized, because typically chemical engineers work for chemical companies that buy reactants and sell the products, and they want to get as much product as they can, so they're trying to maximize the ratio of products. So, and a lot of times they do that by temperature. So guys, do you understand what this is telling you? So what about this? What can we glean? Where's it at? What can we glean about the values for Kf and Kr? K sub F and K sub R. Which one's bigger? Which one's bigger, K sub F or K sub R? How do you know K sub R? K sub R? I'm going to disagree with K sub R. Why am I disagreeing with K sub R? Because our concentration of A is greater at equilibrium. And if our concentration of A is greater at I agree with K sub R. Because our concentration of A is greater at equilibrium, it's this process that's making A, so K sub R must be bigger. Do you get it? Yeah, I've never asked that question before. It's a great question. But guys, it would be K sub R. Because we have more A at equilibrium, that means that this value must be greater, making more A, causing the concentration of A to be greater at equilibrium. Is that okay? You good on that idea? Okay. So now guys, important idea number 2 that you need to understand about equilibrium, and it's this. It does not matter what direction you come at equilibrium from. So guys, allow me to use this little water thing to show you what I'm talking about. So, oh wait, you want to write this down. So, I'll let you write it down and then we'll talk. Can I show you? Yeah. No, heavens no. No, but here's the thing that's cool. It doesn't matter because how do I say this well? While they don't have to be elementary, they always will be stoichiometric. And so we don't need to know the mechanism in order to understand the equilibrium mixture, because it's not based upon the mechanism, it's based upon the stoichiometry of the reaction. So we don't need to know. Okay, so guys, what does this mean on the board? You ready? Join me here. This is how we played this game, right? Jason, Josh, you guys ready? Here's how we played the game. So we had 100 of this. We had 0 of this. We flipped them around. Where did we end up? 70-30, right? What if we did this? What if we started with all product and no reactant, and now we did this again? And so we start, and we've got now a large reverse rate, and we keep going like this. and we go and we just keep going, and eventually this is going to reach equilibrium. And guys, guess where that equilibrium is going to be? Back at 70-30. It doesn't matter where you start. You can start all product, no reactant, all reactant, no product. You can start 50-50. It doesn't matter. You will always end up at the same equilibrium mixture, because the equilibrium mixture is not dependent upon concentration. It's dependent upon the values for K, and the values for K don't change. So guys, you can see this graphically by looking at this reaction. And you actually want to write this down. Don't draw it, but you do want to write it down, and it goes like this. N2 plus 3H2 yields 2NH3. And guys, I should move this arrow because it's in the way of the name. So guys, this is the only named reaction that they expect you to know in AP Chemistry. It's called the Haber process, named after a guy named Bjorn Haber. Some would say that this won World War II for us because we had so many people overseas fighting that we didn't have any farmers left. And they were trying to find ways to maximize crop production so that we could feed everybody while our farmers were off fighting the Germans. And so what they needed was a simple, cheap way to make fertilizer. And guys, if you've ever been on industrial farms, they don't spread fertilizer like we do on our grass. They actually spread pure nitrate or pure ammonia, which is NH3, on their crops. It's the most direct, simplest, cheapest way to get nitrogen into the ground, which causes plants to grow. So they needed a way to create a bunch of nitrogen. Now guys, the problem is that that's hard to do, and actually this drives me nuts. This should be equilibrium. I hate that they didn't do that in the book. But guys, this is a process that actually the equilibrium lies towards the reactants. This doesn't make a lot of product. So they had to figure out a way to get this reaction to make more product, on and on and on. But guys, the bottom line is this. It's called the Haber process, and you just need to, so on the test, they will say the Haber process, and you need to know that it's the synthesis reaction of ammonia from elemental nitrogen and elemental hydrogen. So with all of that said, guys, this is actually, a representation of data collected from the Haber process. So what's the difference between the two trials, A and B? So let's look at A. What are you starting with in A? Bunch of hydrogen, bunch of nitrogen, how much NH3? None, right? NH3 is at 0. Now guys, look at this second trial. What are you starting with? A bunch of NH3 and no nitrogen and hydrogen. But what do you notice when they reach equilibrium? The ratios are the same. That is a representation, guys, of what I just showed you. It doesn't matter if you start with all reactant and no product or all product and no reactant. You will always fall to the same equilibrium regardless of where you start. You get the idea? Okay, so guys, following that then, how do we represent these equilibria? And a couple of you remembered the idea of Kc. Sounds like some of you don't. So we'd better go back and talk about it. So guys, when we represent these equilibria, we represent them mathematically, talking about a ratio of products to reactants. So guys, for this hypothetical reaction that is W moles of A reacting with X moles of B, and that is in equilibrium with Y moles of C and D moles of Z, this is the equilibrium expression. I'll give you a second to write it down. Remember, products go on top, reactants go on the bottom, and the exponents are the coefficients from the balanced equation. As Carson pointed out earlier, we do not need to know the mechanism in order to figure out the values to plug in here because, guys, equilibrium processes are stoichiometric. All we need to know are the coefficients from the balanced equation, and that's plenty to go on. What's that? Oh, if that's the biggest mistake we make today, we're going to be doing great. Yeah. So guys, Carson asked the question earlier, what does the C stand for? Well, guys, this is what is termed an equilibrium constant. You saw that there are at least 6 of them we're going to talk about. The C in this case indicates concentration or molarity, but of course you remember that the brackets in the expression actually are standing in for molarity. And again, because these things are stoichiometric, we don't need to know the reaction mechanism. We can write them directly from the balanced equation. Now guys, last year you solved these. Of course, you'll be solving them this year too, but we're not going to talk about how to do that because frankly, it's just plugging in numbers and pushing your calculator. Or at least that's the case for today. When we start talking about how to solve these on Friday, you're going to find out they become much more difficult. You guys all caught up? You okay? Okay. So guys, maybe what we should do then is why don't you take a look and locate this on your equation sheet and make sure that you see where this is on the equation sheet because you'll need that as a reference. Notice that they also gave you something like this generic equation. But guys, just so you know, and I know that you're trying to think through this, how much work do you need to show when you solve one of these things? And guys, the answer is when you're doing this homework test, whatever, you never need to write this down. You don't have to write down the generic form, but you would need to write down the form that includes the substances that are in the particular reaction that you're looking at. You can't just plug in numbers. You've got to set it up specific to the particular reaction you're studying. So guys, with this as a background, we are also now going to talk about this when instead of talking about aqueous chemistry that therefore have molarities, we can also do this when we talk about gas phase reactions. And guys, you're going to see this in homework in the coming days, that we can also set up equilibria that aren't relative to molarities in water, they're relative to partial pressures in a container. We call these K sub P values, where the P represents pressure and not concentration. And guys, fundamentally, it's exactly the same. I don't even know if you need to write this down. It is on the equation sheet. But guys, what we can do is we can also set up equilibrium expressions where instead of these being molarities, they're actually the partial pressures of gases in a mixture. So this would be, again, products divided by reactants. I don't know where my equilibrium arrow went, but you get the idea. And so this would be C raised to the Y, but now it's the pressure of C, the partial pressure of C, rather than the concentration of C. And it all fits together from there. You guys okay? Now guys, just so you know, this value for Kp is traditionally not the same as the value for Kc. So if you were to find a Kc and a Kp value for the same process, you would find that they're traditionally not the same. You can interconvert between them, but they took the equation away from us to do that. So we're going to take a risk and just assume they're not going to ask us to do that. All right. So guys, that's where we need to be conceptually in terms of equilibrium and in terms of the ratios, products divided by reactants, and how to write them. You okay? So yeah. So guys, what we need to do now is we need to talk about what information is contained in a Kc value. So when we find Kc values, what do they tell us? And guys, this really isn't in your notes, but you may want to write it down just so you have it as a reference to sort of glance at as we're going through this. Where did it go? There we go. Okay, so guys, when we talk about Kc values, keep in the back of your mind that Kc is product divided by reactant. So with that being true, what does Kc tell us? Well, the magnitude, the size of Kc gives us sort of a window into the direction that reactions are going to go. So what about this? And guys, I know this is in the way, but you'll figure it out. So guys, what does it tell us if the value for Kc, when we do this for a reaction, if the value for Kc is really big, what does it tell us about the reaction? Tends to favor which of the two, products or reactants? Products, because if this value, if this fraction is big, that means the numerator is big and the denominator is small, meaning that there's more product than reactant. So if Kc is large, and guys, what does large mean? I mean, we're talking huge, on the order of hundreds of thousands to millions to billions. Like on the order of 10 to the 5th to 10 to the 8th. Guys, if the value for Kc is huge, it tells us that this reaction favors products. And that's the way we say it. It favors products. Another way that you will hear this communicated is the equilibrium lies to the right. And guys, you've got to be able to use both of those terms intelligently. Now guys, what if the opposite is true? What if the value for Kc is itty bitty teeny tiny? It's really, really small. Well guys, if the value for Kc is small, and notice guys please that it doesn't mean negative. Less than 1, but not less than 0. Why can Kc values never be negative? You'd have negative concentrations or negative pressures, and that's impossible. So guys, don't confuse small with negative. This is smaller than 1, but still greater than 0. Well guys, if that's the case, then that means the denominator is larger, the reaction favors reactants, and therefore the equilibrium lies to the left. You okay? Yeah. Yeah, then we would say that that thing is pretty darn balanced. It would be a reaction with almost exactly equal concentrations of both at equilibrium. The bottom line, Eliza, is that what you're going to see is that especially the examples of things that we look at in this class, those equilibria are very shifted to one side or the other. That certainly those things in the middle exist, but typically they aren't things that we'll explore. So, okay. So guys, one more thing. Go ahead, Carson. It could, but not necessarily. So Carson's thought was, Eliza said, what if the value's 2? Doesn't that just mean there's twice as much? And the reason that that's not necessarily the case is because some of these factors are exponential, right? So when we start including the exponents that we're raising these concentrations to, when we factor in those exponents backwards, a K value of 2, if it were, what do I want to say? If it were elementary, if it were unimolecular, the answer would be yes. But if there are those exponential relationships, then the answer would be not necessarily. So, okay, so guys, one last thing we need to talk about. We are not going to get into the last thing we were going to do. So this is where we're going to wrap this up today. So here's what we know. We understand about equilibrium. We understand how equilibrium is dependent upon K values. We understand that equilibrium doesn't matter which direction we come at it from. We'll always get to the same point. We understand how to represent equilibrium as product divided by reactant ratios. We understand what these ratios represent. We call them Kc values or Kp values. Big Kc or Kb values mean that the equilibrium lies to the right. We've got a lot of product. Small Kc or Kp values mean the equilibrium lies to the left. We've got a lot of reactant. Is all that jiving? Okay, guys, the last thing that we need to do is this, and this is important. It has to do with types of equilibrium. Now, guys, remember when we talked about hetero and homogeneous catalysts? That's not this. But guys, you want to get this in your notes in a very detailed way. So guys, when we talk about equilibria, there are what are called homogeneous equilibria and what are called heterogeneous equilibria. But the terms mean the same. What does homogeneous mean? All the same phase. So guys, in a homogeneous equilibria, all of the reactants and products are in the same phase. An example of this would be the Haber process. Hydrogen gas, nitrogen gas, ammonia gas. Now guys, as you might expect, a heterogeneous equilibria then is an equilibria in which the substances are not all in the same phase. And so now you're thinking to yourself, so what? I mean, what does it matter if they are or are not in the same phase? And guys, the answer is going to be surprising. Because what you're going to find out is it radically changes the way that you write the equilibrium. So guys, rather than give this to you in words, let me show you what I'm talking about. So I'm going to go to a fresh screen and we're going to do this together. You ready? So guys, do this with me. Let's do Na ion. No. How would this work well? So Na, let's do, should we do nitrates? I'm trying to figure out how this would work well. Let's do sodium chloride, so Na ion, Cl ion, and then silver nitrate, which would be Ag ion and nitrate ion. Oh, I'm going to have to write the products on another line because I ran out of space, but we're okay. Guys, what are the products? So AgCl as a solid, and then sodium ion and chloride ion, right? No, and nitrate ion. Okay. So say, guys, that we're given this and we want to write the Kc expression for this. So we're going to go Kc is equal to products, AgCl and Na ion and NO3 ion. And then our products, or I'm sorry, our reactants are Na ion, Cl ion, Ag plus ion, and then NO3 ion. Okay? That's the problem. Guys, this is impossible. So let's explain why. So this is dissolved in water, right? It's got a molarity. This is dissolved in water. It's got a molarity. This is dissolved in water. It's got a molarity. This is dissolved in water. It's got a molarity. But guys, this is a solid. It is not dissolved in water. So does it have a molarity? It does not. And so guys, what we do with that is we do not include it in the Kc expression. So when write the Kc expressions for heterogeneous equilibria, you never include solids. Why not? Solids don't have concentrations. You understand? And because solids don't have concentrations, they never go in the equilibrium. Now guys, what about this? Hydrogen gas, oxygen gas produces liquid water. So gas, liquid. What if we wanted to write the Kp for this? Well, we would go Kp is equal to the pressure of water squared divided by the pressure of hydrogen squared and the pressure of oxygen, like so. Do you see the similar problem? What's the problem with what we just wrote? Liquid water doesn't have a pressure. It's not a gas, it's a liquid, and consequently this wouldn't go there. We'd replace it with a 1, and that would be the Kp expression for this process. So guys, the bottom line is this. When you are doing heterogeneous equilibria, because solids don't have concentrations, and because solids and liquids don't have pressures, you never include solids or liquids in your equilibria. So when you're writing equilibria expressions, we never include factors for pure solids or pure liquids. The reason, again, is because these things do not have pressures and they do not have concentrations, and therefore they are not included in the equilibrium expressions. Yeah? They have to be there to balance the equation, of course, right? But because they, and we'll look more at this when we talk about Le Chatelier's principle, because they aren't influencing either the concentration or the pressure of the system, they don't impact the rate, right? If you want to take that all the way backwards, so for example, guys, can I get rid of this for a second? I'll bring it back. But guys, Carson, think about it this way. Looking at this process, as AgCl is created, that is not impacting the reverse rate of the reaction because this is not reacting. It's a product that persists. And so in order for collisions to happen to create reverse reaction, that would have to get involved in the reaction, and it doesn't. And because it doesn't impact the reverse rate, it doesn't show up in the equilibrium expression. Does that make sense? And so here's the point. Yeah, and so, okay, where are we going with this? What you're going to find out is that what we just talked about is going to be an idea that's going to sort of fade into the background until we start talking about slightly soluble salts. Because when we talk about slightly soluble salts, we are then talking about creating a product that then actually does go backwards. And that's, so here's the problem. The reason that this analogy or this example doesn't actually work is because actually this reaction doesn't actually reach equilibrium. I just had to come up with something to give us something to look at. Technically, this doesn't reach equilibrium, and so it's at that point that that example falls apart. So, guys, bottom line here. Do you still need this? No? So let's do this then. What I'm going to do is let me do this. So guys, the last thing that we need to do is we need to talk about what are called reaction quotients. What you're going to find out is not only do K values, you don't need to write this down, not only do K values tell us where the equilibrium lies, K values can also be used predictively. And when we do that, we call them reaction quotients. We're going to do that to start the day on Friday. But what you're going to find out, guys, is when you get into this homework assignment, you are going to find some reaction quotient questions. Skip them. We will make them a part of the next day's homework, and we'll be fine from there. So guys, bring your calculators for sure on Friday. This is where we're going to wrap things up. As you're writing down the homework assignment, Josh, you're going to stay. Bus, Nathan, you are going to stay. Alex isn't here. Spencer Miller, you're going to stay. Parker, you're going to stay. McKay's staying. Taylor's staying. Joey's staying. All the rest of you are free to go for Pride. And guys, we'll get together on Friday, and we will talk about the math of equilibria on Friday.